Start recording. Okay. By the way, if you're ever looking for a video recording and it's not up like that evening, it just means I didn't have time to like organize it and post it that evening, and it should be up the next day. Fingers crossed, but if it isn't, do email me and tell me to get my button gear and get it done. Okay. Especially if you're away, right? All right. So now, what is the molar volume of any gas at STP? 22.4 liters per mole. So if I asked you, what is the volume of 1 mole of propane gas? 22.4 liters per mole. What is the volume of argon gas at STP? 1 mole. 22.4 liters per mole. All right. Now, what if we heat the gas? The particles move faster, and therefore they will take up more space. So you can see here, in the same space, I have fewer particles. If I wanted to have the same number of particles, I would need to have a bigger space for the hot gas, yes? Okay. All right. What is going to happen to the density as we heat it? Whoa, what happened there? That wasn't good. What's going to happen to the density as we heat it? Tell your partner. What do you think? This is page 79. No worries. What's happening to our density? It decreases, right? There's fewer particles in the same amount of space. Yes? So it just has less mass per the same amount of space. That says fewer particles in same. I probably have this written somewhere over here. Let's see. They're more spread out. The volume, blah, 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 blah. Density decreases. No, okay, never mind. Fewer particles in the same space. Therefore, the density is smaller. All right, and here we have, this one was with the same volume. This one has the same, this has a changeable volume. And what happens when we have a changeable volume? The volume will expand as we heat it. But in both, do we have a different number of particles or the same number of particles? Same number of particles. So when we have a changeable volume, we have the same number of particles. So the mass stays the same. But the volume changes. So again, we're going to end up with a lower density. Is this all making sense? Yeah? Okay. Which one has a larger molar volume? The cold one or the hot one? The hot one has a larger molar volume. That's an L. That's a crazy L. Okay. Now, I think we're pretty much good with the fact that I could have carbon dioxide gas, I could have helium gas, I could have chlorine gas, and as long as I'm at 0 degrees and 1 atmosphere, what do I know about the molar volume? They're all the same, and because we're at 0 and 1, they are all 22.4. So they're all the same volume per mole at the same temperature and pressure. If I were to say change the temperature, okay, so now instead of being at 0 degrees, now we are at 20 degrees, still 1 atmosphere. But if I change the temperature for all of them, and you'll notice these are still all the same as each other, even though the gases themselves are different. Yes? And what do you notice about all of the molar volumes? They are all the same. T and P stands for temperature and pressure, okay? So I put stars around this, but I feel like I should have made it bigger, maybe a bigger font, maybe bolder. I don't know. This is Avogadro's hypothesis, and this is important. And Avogadro's hypothesis just takes what we just said here, all the same volume per mole at same temperature and pressure. It just makes it more expansive. It says equal volumes of all gases at the same temperature and pressure contain equal numbers of particles. So it doesn't just apply to 1 mole. It's like if I have 2 moles of every gas at a particular temperature and pressure, it will be the same volume.
So it can be squared.
Yeah, yeah. Now, why is this? Because if you were to look at, let's say, methane gas, right? Let's say we had CH4. And let's say we had helium. The methane looks much bigger than the helium, yes? But gases are really, molecules are more tiny than we can imagine, yes? So if I had a container with CH4, it would look like this. And if I had a container with HE, it would look like this. Except for the dots would be smaller, then I can draw them. Yes? So the actual particles themselves take up minimum space compared with the empty space around them. So the size of the particle or the mass of the particle doesn't really matter. Okay, so the volume of the particle itself is insignificant compared to the space that the gas takes up. It's mostly empty space, and we're just pretending like the actual particles themselves don't take up any volume, because they don't, not a meaningful amount, not until we get to very high pressure and we've squished it together and it's almost a liquid. Do you know what I mean? I didn't get any nods. Did that make any sense? A few of you. Okay. We will be talking about more about this in the gas unit, so don't worry if you didn't quite get it this time. That's okay. All you need to know for this unit is that equal volumes of gas contain equal numbers of particles as long as you are at the same temperature and pressure. Okay, good. And hopefully you did a couple practice problems and examples last night where you learned how to calculate molar volume, yes? Okay, and remembering, if we go back to our yellow sheet, let's go take a look at our yellow sheet. Remember, down at the bottom of the page, this one here, which is sort of like the less complicated looking one, although it looks really complicated once I've scribbled on it. Does everybody have a yellow sheet? So remember, at the top of the page, we're doing conversion. We're multiplying by conversion factors. But when we are at the bottom of the page, if we are finding the molarity, we are dividing, we are doing a division of the moles by the liters. If we're finding the density, we're not doing a conversion, we are doing a division. If we are finding molar mass of an unknown substance, which was the bonus question on your quiz. So the next quiz, I probably won't put that on, but do make sure you know it because it's something I could put on your test. Yes. So if you didn't do the bonus question, what I want you to do is I want you to go home, try it, and then compare with your partner, see how they did, what you got, and then if you don't understand it, come see me. Yes? Okay. Division. And so molar mass is a division, and guess what else? Molar volume is also a division. So you take your liters and divide by moles. You could do milliliters divided by moles. It just depends on what you are asked for. Generally, it's liters per mole. Okay? Okay. So you guys went through these. Did you guys do okay with the examples? Are there any questions about those examples? We are good. Okay. Trying to convert when you should be dividing, that's just like a common mistake. People will be like, oh, I need to find the molar volume and I'm just doing some weird conversion with 22.4 because I know it's a gas and I think that's maybe what I should do. No, if you're asked to find molar volume, you are not doing a conversion like that. So don't use it. Okay, and that was it. This here, I don't know if you guys took... if you guys read this, I didn't assign it because I thought it would be nice to go over it today together. Okay. Determining the molar volume of a gas using an experiment. So we're going to take a piece of magnesium ribbon. Okay, here's our little magnesium ribbon there. And we have our rubber stopper with a hole in it. Okay. One-holed rubber stopper. And we place that magnesium in a solution of HCl. When we start our experiment, So this would be partway through. When we start our experiment, it would look like this. So there's our stopper with a hole in it. There's our piece of magnesium ribbon. Okay, and we've threaded it up there with a copper wire because copper wire isn't reactive. Okay, you don't really have to worry about that too much. But anyway, so here's our magnesium. And at the very start, our HCl solution would go all the way to the top. Yes? Now, over time, what I'd like you guys to do is I would like you to predict the products of, where is a good place to write the reaction? Up here. We have magnesium. What's its state? Solid. We have hydrochloric acid, HCl. What's its state? If it's solution, it is aqueous. Okay, so we have our magnesium solid, we have our HCl, which is aqueous, and do you remember the 6 types of reactions? Tell your partner the 6 types of reactions. Okay, which one is it? Synthesis, decomposition, single replacement, double replacement, combustion, or neutralization? Single replacement, because we have an element and we have a compound. Okay, so this is an element plus a compound. And so the element is going to replace one of the elements in the compound. Tell your partner, is magnesium going to replace hydrogen, or is magnesium going to replace chloride, and why? Does Mg replace hydrogen, or does it replace chloride? Okay, I'm going to teach you the letter for H. Okay, this is H. So you put your 2 fingers and you point them. Yes, that's an H. C, of course, is just a C. So you get to vote whether the magnesium replaces the hydrogen or the chloride. 5, 4, 3, 2, vote. Yes, it replaces the hydrogen. Now, why? Anyone want to tell me why? Yes. Magnesium is a metal. What does that mean? It means it wants to be in the front. Metals always go at the front of formulas. That's one way of explaining it. Does anyone have another way of explaining it? Yes? Yeah, when magnesium is an ion, it's going to be 2+ because it's in group 2. When hydrogen is an ion, its charge is going to be 1+. Okay, and chloride, when it's an ion, what is its charge? 1-. Positive things have to replace positive things because you can't have two negative things together or two positive things together. All right? So now we have magnesium is going to get together with chloride. And what is the formula for magnesium chloride? MgCl2. And I'll let you know right now that MgCl2 is soluble. So what state is it? Tell your partner what it means to be soluble. Soluble means dissolvable. So if MgCl2 is soluble, it is aqueous. And that leaves our other product. Hydrogen has been kicked out. It is now on its own. Do we get H plus? No, we get H2. Because hydrogen is a diatomic element. And what state is hydrogen at room temperature? It is a gas. In fact, at almost all temperatures, you would have to get down to close to absolute zero to make it into a liquid or a solid. I don't know that you can. Maybe you can. I just don't know enough about that. All right. So this is our reaction. What else did I want to point out? What is the charge of magnesium here when it is on its own? What is the charge of the yellow magnesium? Tell your partner. What does it say for magnesium's charge? Nothing. And therefore, magnesium, what charge does it have? Zero. Okay, so magnesium is neutral when it is by itself and when it is in its metal form. Magnesium metal has no charge. Who would it have given its electrons to? It's by itself. Was there anyone for it? Is it in a compound? Can it have given its electrons to someone? No. So if it's by itself, there was no one to give its electrons to, it is neutral. What is the charge of hydrogen here? The blue one. What is the charge of hydrogen there by itself? Tell your partner. What do you guys think? Zero. Yes. Now, should I take a minute to draw the Lewis structures for these? Would that be helpful? Would anyone like to see the Lewis structures? That was a big no. Okay, so I will not draw the Lewis structures. I will trust that you understand why that is zero. Okay, and if you are like, I don't know why it's not 0 and I'm too shy to say anything, come and talk to me like after class or at Flex or something, okay? So we have our reaction here. We are producing hydrogen gas. It's coming up as these bubbles here. Okay, so right here we have the H2 gas, and up above it we also have H2 gas. All right, so let's read what's happening in this experiment now. So the magnesium ribbon is attached to a wire, which is held in with a rubber stopper. As the hydrochloric acid reacts with the magnesium ribbon, bubbles of hydrogen gas are produced. The hydrogen gas collects in the gas measuring tube, which is initially filled with HCl solution. The gas measuring tube has a scale to measure the volume of gas collected. So what it's going to look like is it's going to look like this. Okay, it's going to have like little measurements on it. In fact, would you like to see one of these? Would you like to see a gas measurement tube? Okay, I'm going to hand these out. We're going to take a look at them, and then you're going to bring them back and put them in this box. Okay? Why is it so long? That's actually a good question. Why is it so long? Think about that. Wouldn't it be nice if it were maybe shorter and fatter rather than so long? I need 1, 2, 3. One more. So when you're done, just bring that. Yeah. Magnesium is more attractive to electrons than hydrogen is more electronegative than magnesium. Yeah. And we'll find out why if hydrogen is more it is more or less more stable when they're close to hydrogen than they are. Yeah. At some point this year, we are going to actually do either this experiment or one very, very similar to it. Okay. Now, one thing I want you to notice is that in addition to having this HCl solution, this whole thing is in a basin filled with water. Okay. And that's just to keep the solution in. Okay. And what will happen is that the solution gets pushed out into the water by the gas.
So the gas is the acid out of the.
Yes.
So it goes to the water. So
Yeah.
The water starts to make the acid is going.
The acid is going to end up eventually in the water. Yeah. Okay. But you need somewhere for the acid to go. And you don't want it like just open to air because otherwise it would just fall out. Right? But if you put it in the water, you know how like if you have like a glass of water, have you ever turned it upside? Actually, do you guys want to try this? Okay, we're going to try this. Because you may have done it, but it's not as impressive. So who gave these back? You gave it back. Did you guys give it back? No, who gave it back? Whose is this? No? Oh. Okay, you are going to get yourself, let's see, do we have big beakers? Big beakers. Take a big beaker if you can get one. If not, take a 400. Okay, so one group and grab a beaker. Okay, I'll get out of the way here.
The last word, not very
Now what you're going to do once you have your beaker is fill the beaker almost to the top with water. Not all the way to the top, but almost to the top. There-ish. Once you've got that, you're going to fill the gas collection, that's fine. You're going to fill the gas collection tube with water. And I can only get it about 1 centimeter from the top by using the sink. So I'm going to fill it the rest of the way with a little bit of the water from the beaker. Okay? So fill that all the way to the tippy top. Are you guys not doing it, Brian, Tony? You got water in the beaker. Do you have water now in your tube? You can just use the beaker to pour in there if you want to. It's fine. Pouring from the beaker into your tube is fine. All the way to the tippy top. Then once you have it filled all the way to the tippy top, you're going to put your thumb over it. You're going to put your thumb under the water and you're going to let go. And what do you notice happens with the water? Does it go or does it stay? It stays. So give it a try. Barometers? Yeah. Now, another thing that you can do, once you've done that and you've been like, ooh, ah, exciting. Let's see if this actually works. You can let out a little bit, and then you can lift this up and down and see if the volume changes inside. Does it go up and down? Not all the way out, just like let yourself have an air bubble in there and then bring it up and down and see if the volume changes.
What is happening? What is happening?
I don't know. Is it making a difference for you when you go up and down?
What the fuck?
It's making about a tiny bit for me.
It's chunk of water clumped down full.
At any rate, eventually when you do this lab, I'm going to let out a bunch of the water, okay? Eventually, when you do this lab, if you have collected all of your gas and you want this lab to be like a doable thing, and we'll explain why later, you need this level to be at exactly the same level as the water in the beaker. So I would need to collect more gas because right now my gas is here. So I'll just be like, okay. All right, I'm like, oh, I need to collect more gas. So I would let the reaction keep going, blah, blah, blah. And then I would say, oh no, I have too much, but that's okay. What I will do before I complete my final measurement is I will just lift this up so that it is at exactly the same level. And we'll talk about why that's important later. You can give it a try if you want to, or you can be like, this is frustrating and I don't want to, and you can just put everything away. Okay? So once you're done playing around a little bit, just put it all away. Okay?
No, why would you do it? That's so funny.
Yeah? And if you have more of it out, you just look at that. So it's at the same level. Yeah? Yeah. Well, look at that. Intervention. In action. Does anyone have any questions or any discoveries that they would like to show me? After you're done. Well, after it's even, you will make your so we are going to just let it go.
Oh God.
We'll get more into something. Block is on the desk over here. Let's turn that off so you don't get blinded.
The water surface is there's too little.
When you're done with the tubes, the box for them is right here. Okay?
Do you want it to dry this?
No, you don't need to dry the layer dry.
Why does the why does it replace?
That's a good question. I wanted to talk about that. Because somebody else asked that also.
Like why does it like it's like yeah, so they're saying you're having life and day like
Yeah.
all right, so you got life like the other way around. Like it's like but
Okay, so I've had a question from a couple of people, so I feel like maybe it's worth talking about. And that question was, why is the magnesium able to replace the hydrogen? Okay, why is the magnesium able to replace the hydrogen? Because I can bubble hydrogen through a solution of magnesium chloride all I want to, and it will never go backwards. Okay? And what it comes down to is that magnesium, or hydrogen rather, let's with my pen here, let's make that work again. There we go. Hydrogen is more electronegative than magnesium. Remind your partner what electronegative means. So electronegative is the ability to pull bonding electrons towards itself. So basically what it means is that hydrogen is more attractive to electrons than magnesium is. Hydrogen has more pull on electrons than magnesium does. So what we would have then is we would have magnesium. You remember when you're like, oh, I don't want to see the Lewis structures, I'm going to draw you the Lewis structures. We got magnesium, right? And its valence shell is empty. And we have hydrogen, which, actually, no, sorry, we're starting with magnesium. Okay, that's magnesium 0. And we have hydrogen, whose valence shell is empty, right? And we got a couple of those. And the chloride's just sitting around, not participating, but I'll draw it anyway, just for the sake of completeness. Now, magnesium says, here, hydrogen, you take this electron, and here, hydrogen, you take this electron. Yes? So what we end up with then is we end up with Mg, which has now lost its 2 electrons. It has an empty valence shell, and it is now a 2 positive charge because it lost the 2 electrons. Each of the hydrogens now have 1 valence electron in their outer shell, and chloride is still chilling with like no interest in what's going on whatsoever. Okay?
Well, the hydrogen, right? The hydrogen already gave one.
Now, these 2 hydrogens, are they going to sit there and just be like, I'm okay just sitting here with my unpaired electron? No. So what are they going to do? They're going to get together and they're going to share those electrons between them. So now we have
Hydrogen fold. Sorry, how do you get it?
Now we have MgCl2, and we have H2. Yes? Now, are you going to have to draw diagrams like that? No. Okay? But that's what's happening. And it's because hydrogen is better at pulling the electrons. Yes, and then yes.
So this will be because of the hydrogen connecting with each other rather than magnesium wanting to chloride.
It's more to do with the electrons preferring to be with the hydrogen compared to with the magnesium.
So basically, hydrogen fold magnesium.
Hydrogen pulls magnesium's electrons away from it. Yes? What determines? That's a whole nother subject, and we're going to leave that for a little bit because it's big. Okay, and unfortunately that would take all of today. And we've already strayed away from moles, which is, this is really about quite a bit, but all of this was good. So anyway, back to here, we collected the gas, la, la, la. Here's some data, okay? We collected this many moles of hydrogen gas. Here was the volume we collected. Probably, actually, how would we find those moles? Never mind. Let's just pretend this is the data. We'll talk more about that when we actually get to the gas unit, okay? So we found the moles, we found the milliliters, we know the room temperature, we know the pressure. Calculate the molar volume at 21 degrees Celsius and 0.991 atmospheres. Sorry? We're just going to worry about that in the gas unit, okay? Because it's more complicated than this. Yes? Okay. So, do we really care about the temperature and the pressure for this particular calculation? The answer is not that much, other than the fact that we are not at STP. Yes? Right? Which means that we can't just say 22.4. We have to say, how many liters do I have? Calculate that from your milliliters. And then you will take your liters and divide by your moles, volume over moles, and that gives us our molar volume. Is good? Okay. So that's just a practical example. Solids and liquids. Solids and liquids also have molar volumes, and they all have different. Each solid and liquid has a different molar volume at a given temperature and pressure. So if you have some gold, it will have a different molar volume than iron, than copper, than sulfur. Is good? Okay. So the volume of 1 mole depends upon a couple of things. One of them that it depends upon is how closely the particles are packed. So here is an example of different ways you could pack atoms into a solid. Both of these have 12 atoms. Assuming that the particles in A and B have the same mass, actually I should say same volume, same particle volume. I need to fix that. Which packing arrangement would have a larger molar volume? A. Why?
More spaces in between.
There's more space in between. Which packing arrangement would have a greater density? B, because there's less spaces in between. So basically, as molar volume increases, the density decreases. Due to the lack of space between particles, solids and liquids are not significantly compressible. It's not like a gas where you can squish it. Yes, because there's so much space in between, you can just squish it. So here is an example of a gas. Whoops. Squishable. Right? We basically have the volume. Liquid. Whoa. So tightly packed already, still tightly packed, not squishable. Solid, not squishable. Yes.
Let's say if you have like a mixed amount of weight on the
Sorry, what?
let's say if you have like a lot of weight on it, will it still not be squishable?
If I had less weight on it? Oh, a lot of weight. It would still not be squishable because there's no space to compress. Like the atoms are bumped up right against each other already.
Okay,
Yeah. With a liquid, possibly, although it depends on the situation, right? Like if you have ice, ice is kind of special, right? Do you guys know about ice and how it packs when it is a solid?
Oh yeah, it like expands.
It actually expands. So there's actually more space between the molecules when it's a solid. So if you were to squish ice, like say a skater does when they've got their blade on the ice, right? You will actually make the particles move closer together, which will turn it from a solid into a liquid, which is bizarre, yes? Strange. That's not what normally happens with things, but water is like that. Okay? Solids and liquids do expand upon heating, but the amount of expansion is small compared to how much gases expand upon heating. So, you know, we have a liquid, hot and cold. We have a solid, hot and cold. And if we had a gas, cold, here would be, hang on, gas cold, let's make them red. Gas hot would be like this.
Oh my god.
Here we go. Gas hot, right? Like it's just so much more, right? I can't put it on a page without devoting an entire page to it. Do you know what I mean? Okay. All right. So does molar volume increase or decrease upon heating? Increases. Does density increase or decrease upon heating? Decreases. As molar volume increases, density decreases. Okay, good stuff. Now, molar volume can be found from density and vice versa. So if I give you the density of a liquid, you could find its molar volume. What would you have to do with density to convert it into molar volume, volume over moles?
Mass and balls.
You would have to turn mass into moles. And what else?
All things the same.
Chat with your neighbor about that. So if I turn mass into moles, that would give me, now I no longer have mass, I'm going to put moles there. So that'll give me moles over volume. So that's step one. Chat with your neighbor about that. What would we have to do next? How are we going to go from moles over volume to volume over moles? Moles over volume. Pink pen over blue pen. Moles over volume. How am I going to get volume over moles? Flip it. Yes? You can do that in either order. You can flip first and then convert, or you can convert and then flip. Yes? And if you flip it upside down, then that becomes volume over moles. All right, so say for example, this one, I did this the opposite order. I flipped the density. Okay, so our question here then is, what is the molar volume of iodine, which has a density of 4.94 grams per centimeter cubed? So I said, I want molar volume. Molar volume has volume on the top. So I'm going to put my centimeters cubed. And remember, 1 centimeter cubed is equal to 1 milliliter. So I put my milliliters on the top. And I put my grams on the bottom because I know that I can convert grams into moles. Yeah? And what will I have to do for iodine in order to do that?
It's molar mass.
I need the molar mass. Could you guys please find us the molar mass of iodine? Is it 126.9 times 2 because iodine is I? 2, remember, if you can't remember your diatomics, Dr. Brinklehoff will help you. Yes? It's one of our diatomics. So I2, 126.9 times 2, whatever the heck that is. Okay. Oh, look, it gives it to me here. How lovely. I don't have to calculate it. 253.8 grams, and that gives us 51.3 milliliters per mole. We usually write molar volumes of liquids and solids in milliliters per mole because they generally tend to be smaller. Yes, because everything's so compact. Usually gases, this is more common for gases. Which is liters per mole. Solids and liquids, milliliters per mole. Is good? Okay. So there's some exercises here. You did page 85. Today you could do page 86. How did you guys feel about the exercises on page 90? Take a look at those, see how many you did and how they were for you. 90 to 92, you were supposed to do the odd ones. How did they go? Thumbs up, thumbs down, thumbs in the middle. I got some thumbs in the middle. I got some thumbs up. Okay. If you have questions on it, I didn't have enough thumbs in the middle to go over it in class, but because this is Chem 11 enriched, otherwise I would. But do come in and see me, okay? If you have any questions. I will be here all day at lunch today because I've got a kid coming in to write a quiz. So if you want to stay at lunch today, that would be an okay time. All right, so that was 5.5. What do we got here? Molar mass and density. Did I get you guys to do any of these? Probably not, right? Look at this. What is density measured in? Grams over liters. What's molar mass measured in? Grams over moles. And if we have a gas at STP, guess what? You can convert from liters to moles. Yes? So you can go back and forth between density and molar mass of a gas at STP by using 22.4 liters per mole. Let's take a quick look at the example here. We want to find the density of natural gas, which is methane. Remember, meth contains one carbon, that's CH4. And you might look at that and you'd be like, there's no numbers in that question. How will I find the molar mass? Or sorry, not the molar mass, the density. I'm not given grams. I'm not given liters. But what can I find about methane? What's the only number I can figure out about methane? That's easy. I can figure out its molar mass and I can be like, oh, it is 16 grams per mole, 12 plus 4, right? And so I say I have molar mass of CH4. I want to find liters, so I need to cancel the moles and find the liters, and I want the liters on the bottom. Isn't it good that the liters ended up on the bottom? And that gives me my grams per liter, which is my density. Is good? Okay. The other way it can go about is you might get a result of an experiment. Oh, we found the density of an unknown gas. It was 4.22 grams per liter. What is its molar mass? Well, you can say, I know that molar mass is grams over moles, but I have grams over liters. So I need to cancel my liters and find my moles. Could I do this with anything other than a gas? No. Could I do it with anything other than a gas at STP? Not yet. We'll learn how to do it later for gases at other ones, but for now, this is it. And so you would just cancel your liters and you would find your grams per mole, and there is your molar mass. So your homework is to do page 86. I think it was 86. And then if you didn't do those 90 to 92, do those, but I think most of you did. And you're going to do pages 93 and 94. So 86, 93, 94. If you did not do 90 to 92, do the odds.
We're also supposed to do 96, right?
What's that?
We're also supposed to do 96.
Were you also supposed to do 96? Probably, yeah. Did you do 96? We'll add 96 onto that if you didn't do it, okay? If you did not do 90 to 92, yes? Yes, this will be on the test. Oh, on Teams. Yes, this will be on Teams. Yes. And I think we have 5 minutes, so I'm going to just post that up on Teams. If you want to take 5 minutes and start on something, you can do that. Or if you want to be like, I'm just going to chill for 5 minutes before lunch starts, that is also fine.
Then go to the locker.
Yeah.
What is the one